I want to take a moment to look through the different historical moments of how the system bus evolved, at least for what we would consider the modern PC. So, meaning since the kind of standardization around the IBM clone, at least that's what it was called back then. Now we just kind of loosely refer to x86 architecture, versus say like ARM. But before that, there was more of a divide where there was these IBM PCs, and then there was clones, and then there was basically everything else, like Macs and that kind of thing. But it wasn't until we had some standardization on these platforms that we had any standardization at all. Because before that, you had like kit computers that just had their own proprietary system bus, and there were really one-offs. And it was not even common for, say, like, necessarily different versions of that machine, later versions, to have a bus that it had previously. So things were kind of all over the place until IBM started the standardization with what is known as the AT bus. So the AT bus was a 16-bit bus, meaning that it was a parallel bus that serviced 16 bits at a time, and it was designed for the 286 and 386 architecture computers. There was also a 32-bit processor that you could use with it later on, and they attempted to extend it to 32 bits. This was called Extended Industry Standard Architecture, or EISA. It was a short-lived kind of extension of the AT bus, but it did exist. This bus, by today's standards, was horribly slow. And if you've ever opened up a really old computer, it's interesting. I used to have piles of these things in my basement, when I was younger, and we finally got rid of them. And I'm sure I should have thought ahead. I'm sure a lot of this stuff will be, actually interesting, really worth something now, because people tend to, once something gets 20, 30 years old and it had some importance, all of a sudden it becomes, something people want to remember. But the actual socket for this bus looks something like this, and you would put cards into here. So if you had a modem, which, before we all had high-speed internet, the way that you got on the internet was by having a dial-up modem. So you would actually plug a phone cord into this, and you had a kind of terminal program where you would put in the phone number that you wanted to dial, and it would actually make a connection to a modem on the other side, and you could transfer data. You could also put network cards in these slots. Early video cards would go in these slots, anything like that. And interestingly, if you look at this diagram of the socket, you can actually see like the IRQ lines are in here, the actual data bus lines, and the address bus. And the additional IRQs. So the way this would work is each card would go on the slot, and then, as I mentioned when we were talking about the IRQ, you would actually go into the BIOS of the computer, and you would say, it would notice that there was cards registered, and you would associate the modem, say, with a particular IRQ number, say like 3, and then you would associate the network card, say, with IRQ 4. So that's how you would actually assign these things. You can see that there's also bus lines for power here. There's like a 5-volt and ground. And this is pretty rudimentary, but it definitely got the job done. It also was very slow. I mean, especially by today's standards, this bus had an 8 megahertz clock rate. So even later, like I had an early 386 processor that was a 386 SX, which just meant that there's two versions, an SX and a DX, and it was the earlier, slower version, and it was an SX20, excuse me, which meant that the processor ran at 20 megahertz, but the system bus, as seen here, only ran at 8 megahertz. So there was different clock speeds, which is still common today, between the CPU and the system bus. So remember that system bus controller was operating at this 8 megahertz rate, and your CPU was operating at whatever rate it was. This was actually one of the benefits of this bus. Prior to that, commonly buses ran at the same speed as the actual CPU, and this actually usually acted to hinder the CPU speed. Very often when they put a computer together, they would actually slow the CPU down, possibly from its fastest, so that it could work with that particular system bus. Separating them allowed you to treat them differently and allowed you to let the CPU rock at whatever its max speed was. This is a good kind of example of what the cards looked like. This here is a sound card. This here is a modem. You can see here the jack for the sound, and over here is a little speaker that, if you ever heard a fax machine or you've ever heard a modem connect, that's what you were hearing work. And you would just plug in, there was a couple of telephone jacks here. You'd have the telephone jack in actually, and then you could say plug your phone in. It's kind of acted as an extension so that if you wanted to have your phone on the desk, you still could. And you couldn't use it at the same time. If you picked the phone up, you'd just hear gibberish. But if you weren't using the modem, you could then still use it. This here is actually a graphics card. So not obviously a very fast one, but this is an early graphics card. It actually has two VGA outputs here and its own GPU, as you can see here. Interestingly enough, it had, for the time, it had a lot of onboard memory to handle graphics, but I'm sure this was measured maybe in the megabytes, but more likely in the kilobytes. This over here is a network card. Now, the interesting thing about this is you may not recognize this connector. It's a BNC connector, and this was used for different types of networks like Token Ring, where you would actually connect to the network using a coax cable, and there was both just plain Ethernet versions and Token Ring. Token Ring went in a ring, as it sounds like, but some versions you actually had to have terminating caps. So you'd have these little T-bars that went on the end, and you'd hook the cable up, and if you were at the end of the network, so to speak, you would cap it with a cap. I remember going to friends' houses to play games. This was before the internet, so we would have the equivalent of a LAN party today. I don't think LAN was a term yet then, and we would go and all hook our computers up using these kinds of network cards so we could play each other in games. These are some of the different versions. I mentioned the ESIA before that kind of grew as AT grew. So, by the way, another term for AT is ISA. That's Industry Standard Architecture. And the difference between these is just that one was IBM's and one was not. But when the IBM clones arrived, basically IBM took, problem with them using AT since it was their copyrighted name, even though they had blatantly copied the bus. So they changed the name to call it ISA, but they were effectively the same thing. Here we're looking at an 8-bit, a 32-bit, and an 8-bit, a 16-bit, and a 32-bit card. You can see the 32-bit card, they had to kind of offset them a little bit to fit more in, so the actual trace lines are smaller. The 16, they added another area here for it to connect, so if you ever look at those on the boards, you'll see that some had extra sections. And then the 32 is the same, but if you look, there's a couple of notches here. So you wouldn't be able to fit a 16-bit card into a 32-bit slot because it didn't have the notches. So I mentioned that IBM originally had the AT bus architecture, and that's what was copied with the PC clones. By the way, if you don't know the story of how that happened, it is a very interesting one to follow. There's a common movie on Netflix. It's like a documentary on it. It's a documentary on Compaq. I think it's called Silicon Cowboys. I think that's the name of it. I highly recommend checking it out if you have a chance. It's a really cool look into how that all unfolded. Essentially, what it really came about from is that all the proprietary code that you needed to run a IBM compatible computer was stored in the BIOS chip, and they figured out how to reverse engineer the BIOS, and then they could, figure out how to build the boards, because a lot of it was off-the-shelf hardware. but they needed this BIOS chip. So once they had that, Compaq could actually create computers that could run IBM software, and they used the same bus and all this. And that's how the whole growth came of the IBM clone, and many computers came out of that in the future. But it annoyed IBM, of course, because they had invested a lot of money and they were trying to lock down their grip on the personal computing world, just like they had quite a good grip on the enterprise computing world. So for a next iteration of their bus, they decided to go completely off of the ISA standard. They decided to create something new called Micro Channel architecture, or MCA. This was an extremely fast bus, very fast. In fact, I had a bunch of micro channel machines, but I particularly had a 486 DX4, which meant that basically it was a DX4 100, which basically meant it was a 25 megahertz clock that they overclocked 4 times somehow. I get into that in a whole different talk. But it ran at 100 megahertz, but its bus speed would have been 25 megahertz. So the way that worked is the bus speed on that machine should have been 25 megahertz, and then the processor ran at 4 times the bus speed. So basically they could kind of keep things in sync by doing something once every 4 cycles or something like that. It was very rudimentary by today's standards. The controllers are much more complex today, but that's how it started. This started with a 10 megahertz clock rate, but it was able to go up from there. And it was primarily a 32-bit bus, which was unheard of at the time. It had a 16-bit mode, but it focused on being 32-bit. At the time, it was everything else was the reverse, where it was 32-bit and you might have one special purpose, or I'm sorry, 16-bit, and you might have one special purpose 32-bit slot. Being that IBM constructed, engineered, and planned this thing to work specifically with their own hardware and for their own chips, they achieved really, really, really great speeds with this. In fact, that same 486 DX4 I had, the 100 megahertz chip, that was honestly faster than most early Pentiums. It wasn't until we got well into the Pentium 2 days that I even sunset that machine or considered it a slower machine in any way, shape, or form. Similar to what we see today with how Apple can get more speed out of the iPhone because they can completely control the process, this was a similar thing. IBM really did build a better machine here. It had a greater bus width. It had just more power. Now, this was also, by the way, a parallel bus, just like AT and ISA were. Now, the problem, though, with Micro Channel is that because it was proprietary, you had to buy their items. So, like if I wanted a CD-ROM, which was a popular add-on to a computer back then, you could get, at the time, like I think it was like they came in these intervals like 4x, 8x, 16x, 32x. I think they went up to like 52x CD-ROMs, which meant they were supposedly, every time you doubled that, getting twice as fast at reading the CD-ROM. So in the day when you could say buy a 24x CD-ROM or a 30-something x CD-ROM, I could only get a 2x CD-ROM for my microchannel machine because that's really all that was available, at least at a price point I could afford to pay. And even then, the price was hugely marked up from what you could get in just the PC clone world. So it was much more expensive to have the microchannel machine because the peripherals to buy for it, like a CD-ROM or something else, were much more expensive. And the PC clone market didn't want to pay any of these royalties, so they never jumped on the bandwagon. So microchannel became this kind of thing that had actually led to a stigma on IBM's PC business in a way, because even though it was, by all intents, a superior system, there was this attitude that IBM was proprietary and everything else was free of that, and it kind of branched how they were perceived in a very different way. IBM held on to microchannel for quite a while. The rest of the world obviously needed to move on from ISA because ISA wasn't kind of cutting it anymore. It was very, very slow. It was an antiquated technology, but they didn't want to adapt microchannel, and IBM had made a strong decision that they were not going to go with the herd again. They were going to use a proprietary standard, lock it down as best they could with patents, and try to offer something special. So the rest of the world came up with PCI. This stood for Peripheral Component Interconnect. Intel was actually a big player in helping make this standardization, and you've probably heard of PCI, I'm sure. This was still a parallel bus. We're actually going to only switch to a serial bus when we get to PCI Express. We'll talk to that in a moment. The first version of this was 32-bit with a 33 megahertz clock speed, and it ran with a 5-volt system architecture. Later, they switched it to a 3.3 volt, which for those of you who are electronically inclined, you probably realize that that means you would need completely different peripheral cards probably if they didn't have proper regulation, and that's true. So what they did with the socket is they flipped the way the physical connector was so that there was a divot and you couldn't plug a 5-volt card into a 3.3 and vice versa. So you couldn't fry your cards, but there was a shift there where it kind of made old cards defunct and you had to move to a newer one. They did update PCI over the years, so there was eventually a 66 megahertz bus version of it on a server platform, and then later another version that ran at 133 megahertz, which was even faster. PCI existed for a long time, and it was a good universal bus that allowed the PC clone industry to eventually surpass Microchannel. But it took a long time. IBM had a good jump, but PCI was a good answer. It's just that it came very late. So there was a good amount of time there where IBM had a kind of solid lockdown on having an advantage before they eventually gave it up. By the time we got to PCI, things like interrupts were actually managed by a controller. So you can see here that it has 4 lines for interrupts, and they would be sent around the bus to all the peripherals connected, but the controller would actually manage via a kind of initialization conversation between the peripheral and the controller which interrupts were assigned to which devices. Other than that, this is still a parallel bus, and while it's a little bit more complex, and for the sake of brevity we've kind of denoted just address lines and data lines with bigger blocks here, it still holds all the basic control lines and power that you would expect from this kind of bus. PCI existed for quite a while, and the biggest change to it came when PCI Express showed up. Now, PCI Express is a huge departure from everything that came before it. You might remember when we were discussing buses inside the CPU that we said, due to certain issues, there's a certain point at which a parallel bus is no longer faster than a serial bus. When you, say, take 2 lines and you have a short line here and a long line here, and there's a big difference between those 2 bus lines, that was called skew. And if the skew length was high enough, it messed up your ability to move at a quick rate. It was faster sometimes to have 2 short serial lines, say, or even 1 if it's doesn't need to go in both directions at the same time, and then you can actually just transfer information one right after another. But if the length of that one can be, say it's an 8-bit bus, just for an example, and let's just use raw numbers. If, say, the length of this one was 10 times shorter than the longest one, then you could technically, with no other advantages, which serial does offer, transfer 10 bits in the time that you could transfer 1 over that longer line. Now, you do get additional benefits with serial, because when you remove skew as a problem, you can very often shrink the amount of time between the information moving and settling down, and get even more on that line. And then above and beyond beyond that, you can introduce ideas like compression and some smart ways to move the information, which also helps as well. Another thing that was different about PCI Express is that it was a point-to-point topology. So all devices actually weren't kind of daisy-chained together as they were in the past. They all had a direct connection directly to the hub or the controller. They don't share that bus connection. They all had their own lines. This was another example of why going serial was an advantage. Because you went serial and there would be a lot less trace leads, you could actually now have individual trace leads to all the major components instead of having one that kind of circled the whole board because that's what you had room for. The other thing that PCI Express did is since you had faster serial lines, they decided, well, why not have more than one fast serial connection? So if you've noticed on a PCI Express card before, if you've ever purchased one, there's different X factors. So there's 1X, 4X, 8X, 12, 16, 32, etc. And what we're describing here is the number of serial lanes. These are individual serial bus lanes that you can use to connect that device. So if it's a 1X, it only has one serial bus lane. But if it's a 4X, it has four. So that means in a parallel nature, it can use four serial buses to individually transfer information, and you're getting 4 times the speed. But there's still 4 independent serial buses with all the advantages that come with it being a serial bus and not a parallel bus. You can see here too that the speeds on PCI Express are just insane compared to anything that's come before it. We're now up into, if you had a 16X card, up into the 63 gigabit per second range. You can get quite a bit higher than that as they move through this if you add different amounts of serial lines. Now, they started out with a relatively meager 250 megabytes a second, but you can see that's for the 1X. With every new version, they essentially have been doubling the speed. So 250 to 500, 500 to pretty much 1,000 to 2,000, and now we're up to 4,000. And if this trend continues, PCI Express looks like it's going to continue, at least for now, to be the go-to choice for getting our system bus talking for our I/O components. Another aspect to the system bus is how do we connect things that are outside of the computer. Now, USB, as I mentioned earlier, was a way that we could kind of have a unified bus that replaced a lot of old connections we used to have. I mentioned in a previous video that there used to be a 9-pin serial connector that for really old machines was actually used for the mouse commonly, but it was also called a game port and might have been used for a joystick or any other serial device. You might have had a serial modem or something like that that you connected externally. You had a parallel port, I think that was 25-pin, and that was connected to your printer. That's been done away with for USB as well. You had originally an AT port for your keyboard, but later you had PS2 ports. Those were also replaced by USB. So USB was really a way to kind of take this cacophony of ports that you had on the back of your machine and reduce it to one standardized way to work. Another advantage of USB is it provided power over the bus. So in addition to having a serial bus for data transmission, it also had a 5-volt power line there as well. Now it can only provide 500 milliamps, but it does provide power. So for example, this is how we actually power our Arduinos when we're plugging them in on our USB line. This gave a huge advantage to all kinds of new peripherals that might want to exist in the world, but didn't want to have to figure out how to power themselves. Another bus I want to talk about that's been around for a long time, but not quite as popular as USB, is Thunderbolt. And Thunderbolt is important for a single reason that I really want to talk about that most people don't realize that it even has. This is another serial bus, just like USB and PCI Express. In fact, it is very much like PCI Express because it is in fact an extension of the same bus. So the cool thing about Thunderbolt is that you can actually power PCI Express devices off of it and connect them externally to your computer just like they'd be connected if they were on the internal PCI Express bus, since they share the same specification. It's basically an extension of PCI Express that you can then use outside your computer. You can daisy chain devices with this bus, like monitors, things like that, and it's very, very fast. You can do data transfer rates up to 10 gigabits in either direction.